Hey guys, today I have a 48 volt 100 amp hour lithium iron phosphate battery from Redodo. Apparently I've had this battery for nearly a year now. I was cleaning out my garage the other day and there it was sitting in the corner, still sealed in the original box. If you're watching this, Redodo, I'm sorry. Anyway, Redodo, previously known as Zooms, has a reputation for making some very good batteries. This particular model is 51.2 volts nominal. It's rated for a continuous charge and discharge current of 100 amps. It should have a 200 amp BMS and is rated for at least 4,000 cycles. Now this is a fairly standard plastic case and form factor. We have two M8 bolts on the top for the positive and negative, and we have a carry handle on each side. I ran a capacity test of this battery and it came back at 101.6 amp hours. It's great to see that it still exceeded the rated capacity even after having sat in my unconditioned garage for nearly a year. Now it's been sitting here on my bench for about 24 hours since I completed that test and the BMS has still not turned back on. I find that rather annoying. All of the 51.2 volt chargers I have require voltage to be present before they'll begin charging. Now I can probably find a way to wake it up, such as paralleling it with another 51.2 volt battery and using a resistor, something like that, but I really feel like I shouldn't have to mess with it that much. Typically when you leave these batteries sit, they turn back on and you can begin charging them again. Taking our first look at the battery here, we see the BMS there right on top. This is a 200 amp charge and discharge BMS, and I also see it does say Starry C there. For the wires, we have 4 number 8s for the negative, going out of the BMS and coming into the BMS. The positive is in some fiberglass sheathing here. I do feel it feels like 2 conductors under there. There's also a smaller lead coming off that feeds positive power to the BMS. It looks like we have 5 temperature sensors. I see 2 here going to the side of the battery, and there are 2 more over here. Additionally, there is 1 wedged under the heatsink here, or kind of under the heatsink a little bit. It does appear we have 2 rows of 8 cells each here, and there's a large cable bridging the 2 packs together. There are some large pieces of foam just to protect this battery, which would hit up against the top lid. Our balance leads are bundled nicely, at least on the top here. There is a bundle going around the side, and it's secured at 1, 2, 3, 4 different places at least there. Now it has been 48 hours at this point, and this BMS still has not turned back on. So on the battery side, we are reading 46.8 volts. On the power side here, we're reading 4 volts. So I'm going to try to jump this across real quick here and see if I can get it turned back on. And now we're reading 46.8 volts on the power side. So all we needed was simply a charger that will put a little bit of current in without having to sense voltage. Before I disassemble this battery any further, I want to test the low temperature charge protection. So I did pull 1 temperature sensor off at random here. I have my clamp meter set up. I'm going to turn on a charger. You can see we're charging at about 18 amps there. Go ahead and hit this with some spray. 4 seconds. It took 4 seconds to shut down charging. Let's go ahead and warm it back up here and just make sure it turns on again. And there we go, back to 18 amps. Low temperature charge protection works perfectly on this battery. And this jumper piece is a pair of 6 gauge silicone insulated conductors. In addition to zip ties, this BMS was held down with some very strong adhesive foam, it looks like. It took quite a bit of work, but I finally got the battery pack out of the case. That's one of the few I've had to actually cut the case to get it removed. So with the battery sitting on the bench, we can see it is indeed 2 rows of cells, 8 cells per row, and they are butted up against each other, so we have exposed terminals on both sides of the battery pack. The cells are laser welded together. They appear to be done very nicely. The bus bars are made of aluminum and they have an expansion hump in the center, and they have a dedicated threaded hole for the balance leads. There does appear to be some sort of material between them. I can't tell if that's fiberboard. It's red. The foam padding has punch outs for the vents as well. We have 2 pieces of strapping holding the battery together in the horizontal orientation. And we also have 4 pieces of strapping holding the battery together in the vertical orientation. The QR codes on these batteries begin with 02K, which is an indicator of great power branded cells. And I do believe this is the correct cell model depicted here, and they are indeed rated for 4,000 cycles to an 80% state of health. One thing I do want to note is how neatly run these balance leads are. They're all coming off the bus bar into a bundle. They run across the bottom, and there's another row that run across the top. And they are fixed in place in multiple places with tape, and then they simply run up the side here. Again, very neatly done. Additionally, you can see 2 of the 4 temperature sensors. One is affixed here to the top of the cell, and one is affixed here also to the top of the cell. I cut the yellow strapping here that was going around both battery packs, but I still cannot get them separated. There does appear to be some adhesive foam sandwiched between these two battery packs, which is a great sign as well. So they are insulated from one another on the bottoms. Taking a quick look at the BMS here, we can see the main negative conductors are soldered directly to the BMS. It does appear to be done well. I do wish, however, we would move away from soldered connectors at this point to screw-like terminals, kind of like we see over here. A lot of BMS manufacturers have done that, but this is certainly not a problem at all. So here once again is our temperature sensor. I thought it was landing around here, but you can see it's actually landed in the center of the FETs under the heatsink, which is the perfect location for it. These are the FETs, the transistors that will turn the charging and the discharging on or off. Here we have several shunting resistors. This is how the BMS can determine the amount of current that's passing through the BMS. Basically, it's measuring the voltage drop across the shunting resistors. This is where the balance leads come in, and this is going to be the balancing circuit for each individual cell. And then the rest of this is just the control circuitry. Not a whole lot else to see on the BMS. Alright guys, so there we go. The Redodo 51.2 volt 100 amp hour lithium iron phosphate battery. That's 5.1 kilowatt hours of stored energy. This sells for around $720 as of today's price, the time this video is being posted. Again, I've had this battery for about a year. At $720, that comes out to approximately $141 per kilowatt hour. This battery is built exceptionally well, and clearly they have paid attention to details during the assembly process. One additional point we didn't touch on is that this battery does have Bluetooth, and Redodo does have their own app for it. It'll show you some basic statistics such as current state of charge, current voltage. It shows you if the cells are balanced or not. It doesn't show you specific cell voltages, which I found a little bit disappointing. It simply says your cells are balanced, it says your cells are healthy, but it certainly is a quick way to monitor the current state of charge. Thanks again, Redodo, for sending this out. I will leave links down in the video description if you want to learn more. We are getting close to Black Friday, and I'm expecting to see a lot of battery deals. Even with the tariffs, the price definitely seems to be moving in the right direction. If you have any questions or comments, feel free to leave those. Hit that like button before you go, and thanks for watching.